Dear student, let us discuss lanthanoid contraction today. It is one of the important property of the lanthanoids, and consequences of the lanthanoids are not only on them but on others also. What exactly lanthanoid contraction is, why for it occurs, and what are the consequences of lanthanoid contraction is our expected learning outcome of the today's lecture. A steady decrease in the size of the lanthanoids with increase in atomic number. The size may be atomic size or ionic size. That steady decrease phenomenon is called as lanthanoid contraction. Now about the atomic size variation, the decrease can be shown by this graph. You will find size of lanthanum atom is 187 picometer and size of the last atom lutetium is 172 picometer. So it's the difference of 15 picometer. But there are exceptions. One at europium. See, considerable large size is there for europium, and other at ytterbium. There also large size is there. Except these two, other where we are finding decrease in the atomic size, and this phenomenon is called as lanthanoid contraction. Now question you may be with, why these two are exceptions, students? If you see lanthanoids, who are they? Metals or non-metals? Metals. So metallic bonding is there within them. Metallic bonding is due to free electrons, and free electrons in lanthanum, cerium, and if you come to europium are different. For europium and ytterbium, 2 electrons are the most free electrons, and for other lanthanoids 3 electrons are free. Generally oxygen state is shown as +3 and +2 exceptionally shown by europium and ytterbium. That is also the reason for that. So number of freely available electrons are less in case of the europium and ytterbium, therefore their sizes are larger. Metallic bonding is weaker. Metallic bonding is weaker, then atomic size is will be what? Larger. If metallic bonding would have been the stronger, then atom will come closer. Closer means atomic size will be the smaller. So for other lanthanoids size is smaller, but for europium and for ytterbium the size is larger. So bonding, metallic characteristic is a reason for the unusual increase in size of europium and ytterbium. Now see this graph. It's a variation of ionic sizes. The largest ion is lanthanum +3, and smallest is lutetium +3. Size of lanthanum +3 is 106 picometer, and size of lutetium +3 is 85 picometer. So difference is of 21 picometer. From lanthanum +3 to lutetium +3, there is a steady uniform decrease in the ionic sizes. Therefore, this phenomenon is called as lanthanoid contraction. Now, main question remains. Okay, it is a lanthanoid contraction, but why for it occurs? What is the reason behind that? Students, electronic configuration is a main thing for this lanthanoid contraction. Now about electronic configuration, see this diagram. What you find here, 4f orbitals, which are the characteristic electron possessing orbitals, those are within the atom, those are inside, those are buried inside, and after this 4f orbital or outer than the 4f orbital, there is 5s orbital, 5p orbital, 6s orbital. So orbitals are there outer. So 4f orbital is the inner orbital. This is the electronic configuration. It is general diagrammatic. From quantum chemistry point of view, from a radial distribution point of view, see the electronic configuration here. You will find the, yes, here selective peaks are shown. Peak for 4f, for 5s, for 5p and for 6s orbitals. So from this diagram, it is very clear 4f orbitals are deeply buried inside. Other way are protected by outer orbitals. Now let us see the reasons for lanthanoid contraction. First reason is electrons are added in deeply buried inner orbital, that is none other than 4f orbital. Second reason is, if you see the shapes of the 4f orbitals, those are with many lobes, those are scattered, those are diffused. Due to this diffused shape of the f orbital, they cause less shielding. So it is our second reason. The shapes are diffused. Because of that, this lanthanoid contraction occurs. Now, third reason, from electronic configuration, quantum chemistry diagram or radial distribution diagram, from that what is the conclusion? 4f orbitals are inner orbitals. That is the reason. That's the third reason. 4f orbitals are inner orbitals. Now we have seen the structure for the or shapes of the f orbital. So those are diffused. So and larger sizes they are with. So shielding caused by 4f orbital is less. So less shielding of 4f orbital is a reason for lanthanoid contraction. Fourth reason, from lanthanum to lutetium, atomic number is increasing, means number of protons are increasing, nuclear power, nuclear charge is increasing. Stepwise there is increase in nuclear charge. Now see the last, fifth reason. Because of increase in the nuclear charge, power of the nucleus will increase. And due to increase in power of the nucleus, the electrons will come closer. Atom or ions will shrink. And that is our fifth reason, power of the nucleus increases. If you see the periodic table, in a periodic table, first transition series starts from scandium. That is called 3D series. Second transition series starts from yttrium, 4D transition series. Third transition series starts from lanthanum. It is our 5D transition series. It is found. See the graph now. The 3D and 4D transition series elements, they are with considerable difference in the atomic size. Whose size is larger? 4D element size is larger. But surprisingly, the size of 5D was found to be same as in like of the 4D. It was expected to be larger, but it is what equal. So relative, comparative size of 4D and 5D series elements is a consequence of lanthanoid contraction. Because of decrease in the size, because of shrinking of the lanthanoids, after these lanthanoids, 5D series elements are there. So their sizes were found to be considerably smaller compared to expected size if that lanthanoids would have been not intervening, if lanthanoid contraction would have not been occurring. Because of this lanthanoid contraction, sizes of the 4D and 5D transition series elements are similar. Let us discuss this by one example. Size of zirconium Zr is 159 picometer. it is 4D series element. Now see the 5D series element. Below zirconium there is hafnium, and the size of hafnium is 156, just a 3 picometer difference. Means sizes are considerably same. Okay, it is for atomic size. What about ionic size? Size of zirconium plus 4, because those belong to the fourth group, they can remove 4 electrons easily, so they show tetrapositive cation, tetrapositive metal ion. Size of zirconium plus 4 is 79 picometer, and size of hafnium plus 4 is 78 picometer, just a difference of 1 picometer. So what we can say, sizes are similar because of the similarity in the sizes, and in case of the ions, charge on the ion also similar. It is very difficult to identify, to detect. They behave as like chemical twins. So as we discussed for zirconium and hafnium, similar will be the case for next element, niobium and tantalum, molybdenum and wolfram or tungsten. Likewise, similarities are observed. And this graph is a fantastic explanation for similarity in their sizes. This is a first consequence of lanthanoid contraction. Now, just we have seen the sizes of the 5D series transition and 4D series transition elements are similar. Not only atomic, in ionic states also. So when in a nature these elements do occur, they generally occur combined. And if we need to separate, then chemically it is tough to separate these ions, because both show same charge, both have the same size, both show nearly same chemical properties, and due to that it becomes tough to separate these 5D and 4D transition series elements. Just I used one word for zirconium and hafnium, those are called as chemical twins. So such chemical twins are observed due to lanthanoid contraction. So what was our first point? Similarity in the sizes of 5D and 4D series. Second point, similarity in the properties of 5D and the 4D series elements, making separation difficult. Third point is related to lanthanoids only. What happens in case of lanthanoid due to decrease in the size? Before coming to this point, just see this diagram. Here what are you finding? Sizes of the cations are increasing and anions are same. When cation and anion come close together, because of the positive charge of the cation, anion experiences distortion. Anion experiences change in the shape or the size, and that process or that phenomenon is called as polarization. What do you think? Which cation can have more polarizing power? A smaller cation or larger? No, not larger. Smaller cation will be with more power, because within its small size, that much positive charge is there. So its total power increases, and because of more power, distortion increases, and because of more distortion, covalent characteristic increases or polarization increases. So as we go from left to right, as we go from low atomic number element to high atomic number element, as we go from atomic number 57 to 71, as we go from lanthanum to lutetium, what happens? Size decreases, but charge remains same. All are showing tripositive ions. So size of lutetium is smaller. If size of lutetium is smaller, then what do we expect? Lutetium will cause more polarization or less polarization? Yes, more polarization. If more polarization, then covalent character will be more or less? More. If covalent character is more, ionic character will be less. If ionic character is less, degree of dissociation will be less. Now our point number 3 is change in the basicity of lanthanoids. What is basicity? It is a measure of tendency of furnishment of liberation of dissociation of OH minus ion, and that OH minus ion dissociation depends upon character, ionic character or covalent character. Now just revise. Lanthanum plus 3 and lutetium plus 3. Who has more ionic character? Lanthanum plus 3 hydroxides have more ionic character. More ionic character, more OH minus ion they will furnish. Accordingly, lutetium will furnish less OH minus ion. So basicity will increase or decrease? Will decrease. So decreasing basicity of lanthanoid themselves is because of lanthanoid contraction. That is the third consequence represented here. So what is the conclusion? LaOH thrice hydroxide of lanthanum is more basic compared to LuOH thrice hydroxide of lutetium. Fourth point, it is found in the ores of the lanthanoids. Actually, above lanthanum there is one element in D block, yttrium. It is found, yttrium is yttrium plus 3, occurs along with heavier, higher lanthanoids. See this periodic table. Yttrium, below that there is a lanthanum. After that lanthanoids are there, including lanthanum. Then remaining 5D elements are coming. So what do you think about yttrium and lanthanum? Who will be larger? Lanthanum plus 3 is larger, or lanthanum is larger. So after lanthanum, cerium to lutetium, size is decreasing. So there is increase and then decrease. So by the middle or at heavier lanthanoids, it happens size of the heavier lanthanoids becomes equal to that of the yttrium. So what exactly happened? From yttrium to lanthanum, there is an increase in size. And from lanthanum onwards, there is a decrease in size. So one where the matching occurs, one where the sizes becomes equal. And where the sizes are equal, size of erbium plus 3 was found to be same like the yttrium plus 3. So yttrium plus 3 is 93 picometer and size of erbium plus 3 is 96 picometer. Since their charges are same, sizes are same, properties will be same, properties are same, so they will occur together. So occurrence of yttrium, a D block element, along with lanthanoids, say F block element, along with heavier lanthanoids, is a fourth consequence of lanthanoid contraction. Fifth point and last point is regarding the effect of lanthanoid contraction on post-lanthanoid elements. Now see this periodic table. After this lanthanum, lanthanoids are there, and after this lanthanoids, again the 5D series elements are there, and this 5D series element effect is there on them. What is effect, that we will see. What you noted now, from yttrium to lanthanum, size increases, and from lanthanum to lutetium, size decreases. It is found that sizes of 5D are equal to that of the 4D series element. But atomic number is more. Atomic number increase, number of protons increase, number of neutron increase, nuclear mass increase, atomic weight increase. Atomic weight increase, but size has not increased. So which factor shall we discuss now? Which is related to volume and mass? Yes, density. So atomic density of 5D series element and density of 4D series elements, if we compare, it is found density of 5D series element is almost double than that of the 4D series elements. In first point, zirconium and hafnium that we discussed, that example only I take here. See, after yttrium, the element is zirconium, and zirconium has density 6.59 gram per cubic centimeter. Means almost you can consider 6.5. If you see the element below, which is that hafnium, and this hafnium has the density 13.3 gram per cubic centimeter, means near about 13. So here 6.5 and 13, almost double. That I wanted to say. Density of these post-lanthanoid element is almost double than that of their predecessors, 4D series element. It is because of lanthanoid contraction. One additional thing I informed to you. Since nuclear charge increases, but size of the atom has not increased, and size of the atom is not increased, therefore there is a hold of the nucleus on the outermost electron. These elements, post lanthanoids, are considerably inert. Inert means the sense they do not involve in the. These are metals. They should give the electron, but the tendency to give the electron is less because size is smaller and nuclear is more powerful. Therefore, if you see the element here with atomic number 79, what is that? Gold. Gold is gold because of lanthanoid contraction. Gold is valuable because it is not reacting. It is not reacting because there is a hold of the nucleus on what the outermost electrons. Okay, it is additional point that I told to you. So students, is the point of lanthanoid contraction clear? After this, these lanthanoids, how do occur in nature and how can we extract them? We will see in the next part.